Good afternoon. I'm Yunkai from UC Berkeley. I'll present our work towards VM rescheduling optimization through deep reinforcement learning. This is joint work with UC Merced and ByteDance. To start, let us talk about what are virtual machines. When you request some CPUs or GPUs on a cloud service provider, they don't ship you a physical machine. They let you connect and use the physical machines, or the PMs, remotely. Actually, you might only need a portion of the resources on the physical machine. What happens is resource virtualization will allow each physical machine to host multiple virtual machines independently. So whatever you do on your own virtual machine is not likely to affect the other virtual machines hosted on the same PM. But if there are multiple VMs currently deployed on a PM, the amount of resources left over on the PM might not be enough to handle additional VM requests. In this case, the amount of resources that cannot be used is called fragments. So when managing a data center, a key question is, given the fixed set of physical machines that we have, how do we fit as many virtual machines as possible? We can formulate this into a high-level objective. For example, we might want to minimize the fragment rate, or we can minimize the number of migrations that we need to achieve a specific fragment rate. So VM scheduling is when a new VM request arrives. We select one PM from all available PMs to host that VM. From first look, this might seem to be very similar to the famous bin packing problem. We try to put items, which are virtual machines in this case, into a set of bins, or the physical machines. Indeed, just like bin packing, this problem can be formulated as a mixed integer programming problem. However, there's one difference. As the data center gets bigger and bigger nowadays, there can be many virtual machines entering or exiting the data center at every minute. So the algorithm must be very quick. In fact, only heuristic methods can satisfy this level of latency requirements for VM scheduling. So if we look at the plot in the middle, the green line here will indicate the latency requirement for VM scheduling. Since we can only use heuristic solutions for VM scheduling, these heuristic solutions are often suboptimal, and together with the continual exit of completed VM jobs, they can create many fragments across the cluster. This is where VM rescheduling comes in. However, just like VM scheduling, rescheduling also needs to be very quick, since the cluster state is also changing dynamically. If it takes too long to compute a solution, some migrations might no longer be feasible. Fortunately, unlike VM scheduling, which needs to be run throughout the day, we can choose when to perform rescheduling. In practice, we often choose to perform it during off-peak hours, such as in early mornings, where the cluster state doesn't change as quickly. However, the latency requirement is still very high. In fact, let's do a motivation experiment to quantify how the inference speed affects the achieved performance. This will give us a sense of how quick our algorithm needs to be for VM rescheduling. We can actually formulate the VM rescheduling problem as a mixed integer programming problem with some constraints. The issue here is that the solution space is very big. A normal cluster can contain as many as 2089 VMs and 280 PMs. If we use a MIP solver, it will take up to 50 minutes to deliver a near optimal solution. Recall that when the MIP solver returns the solution, many of the VM states have already changed. In these cases, these VMs might not be migrated. So assume that we can actually get a near optimal MIP solution in less time, and we measure how the amount of computation time affects the number of VM migrations that can still be valid, which in turn affects the final achieved solution. In this figure, we see that if the solution can be returned within 5 seconds, there is only a minimal increase in the achieved fragment rate. However, if it takes over 5 seconds, the achieved objective quickly becomes worse. Therefore, we aim to develop an algorithm that can return a solution for any given VM to PM mapping within a 5-second limit. Many existing MIP solutions often perform approximate MIP or some kind of searching, which fails to meet the latency requirements. Instead, what we propose here is a deep reinforcement learning-based solution called VM-R2L. Reinforcement learning is a good fit here for 2 reasons. First, there are no aleatoric uncertainties in VM rescheduling. That means the next state can be exactly simulated given the current state and action. RL is often notorious for its poor sample complexity. However, since our environment is deterministic, we can instead build a simulator. We only need the initial VM to PM mappings for training, without having to interact with the real data centers. Second, the generalization power of neural networks allows us to train the agent offline, and the agent will adapt to the production environment without having to do any fine-tuning or retraining. This is unlike existing MIP solvers, which often need to recompute the solution from scratch given a new VM to PM mapping. So how do we formulate the VM rescheduling problem as a reinforcement learning problem? We can define an episode to be one VM rescheduling request, where each step in the episode means to migrate one VM. The state at each time step is a vector containing some customized features for each VM and some customized features for each PM. To migrate a VM, we need to first choose the VM candidate. Based on the VM candidate, we can infer the current PM machine that it's deployed on. Then, we can select a destination PM. In this sense, the action takes form of a 2-tuple. Assuming the end goal here is to minimize the change in the fragment rate, we can construct the reward to have a direct correspondence with the final goal. This makes the learning process much easier. For this reason, we set it to be the change in the fragment rate on the source PM, plus the change in fragment on the destination PM. And because given the current state and action, we can exactly simulate what the next state will be. The transition function here will be deterministic. And of course, the end goal here is to minimize the value function, the discounted cumulative reward throughout the ML steps, and the MNL here stands for the migration number limit. So the first component of VM-R2L is the 2-stage framework. When the agent chooses to reschedule a virtual machine to a new destination PM, the destination PM might not always have enough resources to host the VM. In practical scenarios, some additional constraints might be enforced. For example, we might have a hard anti-affinity constraint, where some VMs cannot be hosted on the same physical machine. This constraint is often enforced in practice because in the case of one physical machine is down, we might still have some backup VMs for that job running somewhere else. These types of constraints will cause some of the action tuples to be infeasible. Existing methods often give the agent a heavy penalty if a legal action is taken, but the penalty will likely dominate the reward signal at initial stages of training and causes a slow convergence. Alternatively, some methods might choose to mask out the illegal actions entirely. However, the total number of actions is the number of VMs times the number of PMs, which can be too big to compute a mask for. Instead, we propose a solution tailored for VM rescheduling. We break down each action tuple into 2 stages. In the first stage, we choose a VM candidate, and based on the selected VM, we can safely mask out all illegal PMs. Then, at stage 2, we can choose a destination PM from all the remaining PMs. Besides avoiding illegal actions, they can also effectively reduce the large action space, allowing our model to converge much faster. And the second component of VM R2L is feature extraction with sparse attention. To make effective rescheduling decisions, we must extract meaningful representations of the state observation, which include features of each individual PM, and as well as each individual VM and their affiliations. However, as we showed earlier, the number of VMs can vary a lot throughout the day, even in the same data center. This implies that the size of features at each time step is also highly dynamic. To encode these features, one option is to concatenate the features from all VMs and PMs together into a very long vector. However, this approach cannot handle an arbitrary number of VMs, as neural networks usually require fixed-size inputs. And if we use zero padding to make the input at each time step to have the same size, it will require a model with many parameters that would be difficult to train. Instead, we propose to share 2 small embedding networks across all VMs and PMs, one to process each PM's features and one to process each VM's features. As such, the number of weight parameters is independent of the number of machines in the system. This is achieved via an attention-based transformer model. However, we don't want to use a transformer model directly from the shelf because something is missing here. Note that compared to bin packing, in VM rescheduling, we must choose from a set of VMs that have already been assigned to the PMs. Therefore, it's important for each VM to know which other VMs are hosted on the same PM, and each PM should also know which VMs it currently have. To do so, we propose to modify the vanilla attention mechanism by adding an additional stage of sparse local attention within each PM tree. That is, we only allow PMs and VMs to attend to each other if and only if they belong to the same tree. And the third component of VM R2L is a risk-seeking evaluation pipeline. Given an initial state and action sequence, we can exactly simulate the end reward. So this means that we can actually sample multiple trajectories at inference time, and we can simulate the end reward and only deploy the one with the highest reward. And some future work might be to accommodate this into doing training also with the risk-seeking objective. And we show 2 lemmas here. The first one is how the number of trajectories we sample at inference time will give us different achieved final rewards at the end. This will allow us to balance between the inference speed and solution quality. And the second lemma is that because we want to sample from a distribution instead of always taking the argmax from the objective, we will try to mask out all the actions that are assigned very small probabilities, which are likely to be suboptimal. And we call this action thresholding. And in experiments, we show that both components are critical for risk-seeking evaluation. And now let's take a look at experiments. The first one is how our algorithm perform in terms of the objective and the inference speed. We consider 6 main categories of baseline that are typically used for bin packing or job scheduling. And we limit the inference time of all methods to 5 seconds. We see that our algorithm is able to achieve a performance that's the closest to MIP while maintaining a competitive inference time. Due to the limit in inference time, approximate algorithms combination-based algorithms, and search-based algorithms all fail to deliver good solutions. The learning-based algorithms does not use any of the custom design features that we tailored for VM rescheduling, and thus also behaves poorly. And here, we also perform an ablation study that shows that both the sparse attention as well as the reseeking evaluation are critical to our framework. And we also show that our solution can accommodate different objectives, such as what if given a specific fragment rate goal, we want to minimize the number of migrations, or if instead of having a fragment rate, we can have also like objective defined in terms of both fragment rate and resource constraints. And then also accommodate different constraints in addition to just resource constraints. For example, we can also have a service affinity constraint. And we also show that our framework is robust to distribution shift. So here we synthesize 3 datasets with non-overlapping CPU usage. And we show that if we train our algorithm on 1 or 2 of the datasets, it can generalize well to the 3rd dataset. And due to the sake of time, we also performed some additional experiments in the paper, but I will skip here in today's talk. And lastly, where do the improvements come from? We see that sparse attention allows each VM to see which other VMs are deployed on the same PM. And the cumulative reward in RL and risk-seeking evaluation allows the agent to sacrifice some intermediate reward for some long-term performance. So in particular, in this figure here, from step 38 to step 39, the agent actually chooses to not make any reward. But the reason that it did this is to get a bigger reward from step 39 to step 40. And this is all I have to talk about. And our code and dataset is available at this link.